Good afternoon, guys. How's it going? Today we'll be doing some more physics as per usual. Questions 25 and 26 of the HSC Physics of the 2017 HSC Physics paper. Okay, let's get to it. Question 25 asks this: outline the contribution of the Braggs to the scientific understanding of materials. This is a pretty simple answer. It's only it's a 2-mark question, so it means there was two things that sort of were involved there. Two ideas we have to talk about. The Braggs were the first to use X-ray diffraction. That's the first bit. And they were the first to use X-ray diffraction to discover the structure of crystalline materials and explore the crystal lattice. So that is a pretty important part of it. So you can talk about crystalline materials, crystal lattice, and X-ray diffraction, and that should get you 2 marks for that question. Okay. Question B asks, explain how doping pure silicon with boron changes its electrical properties. So we should remember from our physics study that pure silicon is a semiconductor and that it does not conduct well at room temperature. This is because it only has 4 electrons in its outer shell. Adding a group 3 element like boron adds a hole to the crystal lattice, and that hole is a gap which can be filled by electrons as they are applied to, as an electric field is applied to the silicon, and that allows current to flow through the semiconductor. So things to look for there. So we need to explain how doping pure silicon with boron changes its electrical properties. It's only a 2-mark question. It's not too big. So first thing we do is that we talk about why pure silicon doesn't work well, or why it's not enough on its own to be a good conductor. And then we explain the benefit that boron has. The first thing we say is that boron is a group 3 element, and because it's a group 3 element, that means it only has 3 electrons in its outer shell, in its valence shell, and that's what provides that gap when silicon is doped with boron. Okay, so we've explained the difference between silicon and boron, and we've explained how it benefits it. So that's going to be our 2 marks right there. Question C. Outline reasons why superconductors are used on board maglev trains. So this is a 3-mark question, and we need to make sure we answer all parts of it. So we need to outline reasons. That's probably going to be maybe 2 or 3 reasons. We need to talk about how they're used on board the maglev trains. So superconductors are able to produce larger magnetic fields than naturally occurring magnets. The strong magnetic forces between the rail and the carriage allow levitation to be achieved, which significantly reduces resistance. Superconductors are relatively light compared to natural magnets and have to be kept cool at less than 95 Kelvin. This makes it more efficient to keep the cooled superconductors on board the carriage to produce levitation. So the things to think about there is that we've got superconductors are able to produce much larger fields than naturally occurring magnets. And they produce that through using electromagnets. So they're basically just giant electromagnets. The next bit is we're thinking about, well, why are they used? And they do that because you can achieve levitation with superconductors, and that reduces resistance between the train and the track. And then we can say, well, these superconductors would be much lighter than the natural magnets that would be required to achieve a magnetic field required to levitate a train. So the disadvantage, though, of superconductors is that they have to be kept cool. Now, you can have a superconductor on a track and have a natural magnet or natural metal or whatever inside the or magnet inside the train, but that would mean you have to keep the entire rail cool rather than just the superconductor inside the train. So having the superconductor inside the train being kept cool is much more efficient, and that's why we do it that way. So that's what's happening there. A little side note, guys, and a little pet peeve of mine is that, because I did study in superconductors, and something I didn't realize until I studied this myself and started doing a bit of research into superconductivity, is that the cool videos we see about superconductors levitating above magnets is a certain type of superconductivity, and that's when it's in the Shubnikov phase, as it's called, and that's when you have magnetic field penetrating a superconductor. There aren't any trains that utilize that effect, but there is another effect where we can have very well balanced magnetic fields And that can be achieved through using a superconductor through the Meissner effect. And that's what we study in high school. We study the Meissner effect. But that is not the same as superconducting levitation. That is just an effect of magnetic levitation. So that's an important thing to be aware of. Is that relevant to the HSC? Not too much, but it does become more relevant as you get more advanced in your superconducting studies. Okay, so that was question 25. Question 26. Outline consequences of crewed spacecraft re-entering Earth's atmosphere at an angle greater than 10 degrees. So notice that it's a 2-mark question, so that means we're probably going to need at least 2 consequences. So we should know that the optimum re-entry angle is between 5.2 degrees and 7.2 degrees. So at an angle greater than 10 degrees, obviously greater than 7.2, the spacecraft will decelerate too quickly. That's one thing. That's going to put a lot of forces on the astronauts. As it decelerates too quickly, it will encounter too much air resistance, and that extra air resistance will cause a lot of heat to build up, and the spacecraft won't be able to dissipate that heat fast enough, and that will be too much for the spacecraft and passengers to survive. So there's our 2 consequences: decelerating too quickly and too much heat. That's what we're going. So question B. When the 100-ton space shuttle re-entered Earth's atmosphere from its orbit, the gases compressed in front of the decelerating shuttle reached a temperature of 5,000 Kelvin. The graph shows the intensity of radiation emitted by gases at 5,000 Kelvin. Relate the information in the graph to the energy changes required for the shuttle to make a safe landing. Okay, so this is a 4-mark question, so we need to make sure we answer every part of this question. Okay, relate the information in the graph, so that's one part, to the energy changes required for the shuttle to make a safe landing. Now, what might seem really obvious, but you might not think to include it in this answer, is that to make a safe landing, we need to reduce the kinetic energy of the shuttle before it lands. If you don't reduce that kinetic energy, it's going to have a bad time, and the passengers inside will also have a bad time. Okay, so that's one part we're going to need to think about. Another bit to think about though is we're going to relate the information in the graph. So the information in the graph is saying that the bulk, well, I'm not going to say the bulk, but the peak intensity of radiation is in the visible spectrum. It's in the visible spectrum here. And then we can say, well, first of all, let's read this. So the peak radiation intensity emitted is in the visible range, with a large amount also in the IR band. For a safe landing, the spacecraft needs to slow down. As the spacecraft slows down, gravitational potential energy and kinetic energy is being converted into heat and light energy and is being radiated away. So we've got the peak radiation in the visible spectrum at 5,000 Kelvin, but we can also say, even though it's not indicated on the graph, that all of this area is actually infrared radiation as well, up until about 1 million nanometers, which is about 1 millimeter. So I should say, so yeah, at a wavelength of 1 millimeter, then we reach the next band from infrared, which is microwaves. It should be, yeah. Cool. So the peak, almost all of the energy that is being emitted, so that's emitted, not reflected, being emitted by the space shuttle, is in the visible range, and it's in the infrared range, which is the heat, which is basically heat. So the peak radiations that the space shuttle wants to get rid of is heat and light. And that's and the source of that energy, the source of that light energy, is going to be the kinetic energy as the space shuttle is entering the atmosphere. So that kinetic energy, as it rubs up against the atmosphere, is being converted into heat and light, and that's getting radiated away after that. And that energy being radiated away means there's a reduction in the kinetic energy of the spacecraft, which means it's slowing down. So that's question 26. I believe that's it. It is. All right. So guys, that's been questions 25 and 26 of the 2017 HSC Physics paper. Hope you guys have a good day and hope that helped. If that didn't help, please leave a dislike in the comments below, and please leave a dislike and a comment below explaining how I can do some of these things better. Alrighty guys, have a great day.